0, so it is so perfect quadratic, VIF equal to infinity. Okay, that's one. Then take note that the R square used in the above formula come from the now that each of x equals against x. So R square of 0 is negative non-multiplicativity and all produce VIF equal to 1. So if you regress x and each of x against x, you produce R square equal to 0, then the VIF equal to 1. So there is no problem of multi-quantity problem at all because the value is equal to 1 because this 1 minus 0. So the variance inflation factors measure how much the variances of the estimated regression coefficient are inflated as compared to when predicted variables are not linearly related. So it give kind of what we call an indication or just estimate how much the value of the variance of the estimator increase or inflate as compared to if there is no multi-quantity problem. So this is an example, the same example data that we used just now, the one that we used just now. So we have consumption, income and wealth. Let's say we want to construct a model to explain consumption using income and wealth. Okay, income and data of monthly consumption, monthly income INC, and wealth WLTH. So you can inspect the correlation between two. So basically the first step, if you inspect the cross correlation between the variable, that can give you an idea whether there is high possibility to have serious problems of multi-quantity or not in the model. So let's say we have data here. So we have this data. So you open as one the example. So here our independent variable consumption. We have two independent variables, income and wealth. So the good practice is that before you estimate, you inspect the cross correlation between your independent variable in order to see again the correlation, because correlation can give an idea about the possibility of having serious multi-quantity problem in the model. So you can go to, let's say you go to quick group statistic correlation. So I hope you already know the concept of correlation. What is correlation? Correlation represents association between two variables. Okay, remember the scatter plot. When x increase, y increase, that one correlation positive lah. So when x increase, y decrease, in that case the correlation negative. Okay. So correlation, you can just type the list of independent variables we have. So income and wealth, WLTH. Okay, then okay lah. So you get correlation. This is what we call as cross correlation. Cross correlation table. So correlation between income and wealth is given here, 0.998,962. So quite high, so almost 1. Remember correlation take values between -1 to +1. So this one close to +1. Okay, so again, so meaning that we have to be careful lah. So when you regress, you estimate regression model or regression model, you have to be careful for the possible present of serious problems of multi-quantity, because there is high correlation between the two independent variables. Okay. So and then we regress and see, you regress, we see that, okay, so another thing that you should do when, before you estimate model, you should state, or you should identify the prior expectation, the sign of the prior expectation of about the sign of the estimate. So let's say, income and consumption. What is it? What is your expected relationship between consumption and income? When income increase, consumption is supposed to be increase or decrease? Increase, lah. When income increase, we expect consumption for that. Consumption also increase, so we expect the estimate to produce positive, lah, to have positive estimate of the slope. And then wealth and consumption. Health, what we call that richer person supposed to consume more, positive as well, lah. Okay, so we expect wealth also to have positive effect on the consumption. So both positive, income positive, wealth also positive. So we have now, before we estimate, we already have that in our mind, whether it's supposed to be positive or negative. If you're not sure, you can check the previous. You can check the theory, for example, refer to the theory, or you can check the previous study in order to see what is the supposed to be what we call that relationship between dependent variable and independent variables. So after we estimate, you can see that income positive, okay lah, but wealth has negative estimate. So meaning that wealth have a wrong sign. It's not as what we expect. Okay, it is negative, although we expect to be positive. Okay, so overall test shows that model is significant. Okay, you estimate model. So this one, we estimate model. You go to quick estimate equation. Quick estimate equation. Okay, so you type the variable that we have. So we have assumption, then C for intercept. Remember C for beta 0 intercept. And then we have income, INC, and then wealth, LDH. Okay, so we get this estimate. So this estimate for the beta 0, estimate for beta 1, estimate for beta 2. So just now, as I mentioned, as stated in the note, for income it is okay, but it is not significant. Here p-value greater than 0.05. So we do not reject. So we say that there is no significant effect of income on consumption, right? Because p-value greater than 0.05. For wealth, although for wealth the estimate, the sign of estimate already incorrect, negative, although it's supposed to be positive. So it's not what we expect to see. It is negative, although it's supposed to be positive, and in terms of p-value, it also not significant. So both insignificant, greater than 0.05. So again, there is another sign of one of the sign of the serious problem of collinearity between independent variables. And then if you compare to the F test statistic, this one, F test statistic as well as p-value for the F test. So p-value for the F test 0, it is less than 0.05, so we reject. Remember, for this F test we use to perform the joint overall significance, for the overall significance of the slope parameters. So beta 1 equal to beta 2 equal to 0 for this case. Both slope beta 1 and beta 2 equal to 0. Alternative, at least one of them are equal to 0. So this one, based on this result, we reject and we conclude at least one of them not equal to 0. But when you compare to this one, it is inconsistent, right? Because this one both insignificant. both not significant, but this one says F test says at least one should be significant, but this one both not significant. So you have contradictory conclusion between F test statistic and the individual health testing using t-test. Okay, and then R square also. R square high, right? Yes. Both the two variables not significant. So again, the overall significant test shows that the model is significant based on F test. However, none of the absolute coefficient is statistically significant based on the t-test. Another way to check the presence of serious problems of quantity is by looking at the VIF. Okay, so if used, you can easily produce VIF by going to view, coefficient diagnostic, select variance inflation factors. After you estimate the model, you go to view, coefficient diagnostic, variance inflation factors. Okay, so you get this one. So how these two values are obtained? For the case of whenever we only have two x, when we only have two x in the model, then we have the same values. If we have more than two, then we have different values. So this one, as explained, let you know how these values are obtained. It's obtained by regressing each of x on other x. And then we get R square, and then you calculate 1 divided by 1 minus R square. So for example, this one, so let's say, how we get this one? 482, it's obtained by regressing income on wealth. Or wealth on income, we get the same R square. Whether you regress income on wealth or you regress wealth gain income, you get the same R square. That's why we get the same VIF. If let's say you have 3 variables, and then you will get different values of the VIF for each of variable. So this one, if you regress, for example, you regress income INC against wealth. Okay, just name to save the earlier one. So you see this one, when you regress incomes against wealth, the R square is 1, and then you calculate the given formula. This one, 1 over 1 minus R square, and then you get, so here we get 500, basically, the exact value, the one, this one because we round out the value of R square. So we get about 500. So basically, if you get 482 just now. So basically, that's how we get the VIF. So you regress one independent variable against other variables. If let's say you have 3x, then you regress this variable against the other 2x. Okay, not only one, but the other rest of the x in the model. You regress each of x against the rest of x in model. If they are 3x, then you regress one of x against the other 2x. Okay, and C plus C, then x2 space x3. Then you get R square, then you calculate the formula 1 over 1 minus R square, then you should be able to get this one. Okay, VIF factor. VIF. So this value clearly greater than 10, so that indicates that there is very high collinearity between the two variable, independent variables x1 and x2, income and wealth. So there exists serious multi-quality problem. Alright, so there are two important points should be emphasized here, or you should remember, or you should understand. First, multi-collinearity does not cause the regression coefficient to be biased. Their probability distribution are still centered over the true values if the regression specification is correct, but they have unsatisfactorily large variance. Okay, so the sampling, the presence of multi-collinearity will make the sampling distribution for the expected to be larger. So let's say we are estimating this model, beta 0, x1, error. So we can take, this is the true value, but normally we do not know. So we just take sample and then we get estimate, and then we estimate put hat, beta 0 hat, beta 1 hat, beta 2 hat. So the true value, bias, remember I explained to you what's the meaning of bias estimator? Unbiased estimator. Unbiased estimator when the average, so this is the, when you estimate from a sample, let's say different sample will give you different estimate of beta hat, beta 1 hat. This is what we call sampling distribution for the estimator. So we use the ordinary square to estimate the true value beta 1. This is the true value beta 1, but we do not know now. This is for population, just like mu and x bar, then the same concept. Mu we do not know. So but we take a sample, we calculate the average, that's our sample mean x bar. So it's the same concept lah. So this is the true relationship between y and x in the population. Y and x1, x2 in the population, the entire population, but we do not have access to all elements in the population, so we just take a sample and then we estimate, and then the estimate we can have different values, can be here, can be here. Okay, so unbiased estimator means that the average of all possible estimate equal to the true value, then it is unbiased estimator. Okay, so the presence of, if let's say this is the case of if there is no multi-collinearity, but then we have a situation we estimate, but there is multi-collinearity, the presence of multi-collinearity will make the variance of distribution to be larger. Okay, so we have larger with the presence of multi-collinearity problem. Let's say our x and x1 and x2 has high correlation between them, then we will make the distribution to be larger, sampling distribution to be larger. So this is still same, although it is still unbiased, but it has larger variance lah. Okay, so it has larger variance. So it is still unbiased, meaning that the average of all possible estimate still equal to the true value of parameter, but what the presence of multi-collinearity will make the distribution sampling to be larger. So meaning that there are more possible, wider possibility of estimate beta. When we take a sample, previously just between this from here to here, the possible value of estimate. But now when you take a sample, it's possible you get here very far from the true value, or you get here, okay, very far from the true value. Yeah. So that's the problem of having the effects of, or implication of having multi-quantity problem. Second, the standard errors and t-test remain valid, although it is still valid, but it is not less reliable lah. So because we have however, the standard errors are larger than they would have been in the absence of multi-quantity, warning us that regression estimates are erratic. So because it makes the standard error to have to be larger, like I mentioned before. So we have a tendency to we are more likely to not reject the null hypothesis. Okay. If you recall back what we discussed earlier, where it is here. This one, huh? Recall that how we calculate the test statistic using the formula that I explained before. This one, the T, we calculate this one. So when the present of multi-quantity will make the standard error to be larger, so that the T statistic is going to be smaller. Smaller. So this is larger, so the whole T smaller because we divide by larger values. When T becomes smaller, then we are more likely, because T moving here to the center, smaller T, smaller T. So we are more likely to conclude that there is no significance. So we are more likely to do not reject the null hypothesis and conclude that the true value is equal to 0, while the fact that it's not equal to 0. Okay. So it make it increase the chance for us to make incorrect conclusion. Okay, so we say that there is no significant effects of X on Y, but in reality there is a significant effect. But because of the present of multi-quantity, now we make incorrect conclusion. Okay. So how to overcome the problem? What is the option that we have to remedy the problem? So the first option, just ignore the problem if the problem is not that serious. Okay, remember the implication of having serious multi-quantity, it makes our estimate to be incorrect, the standard error to be larger, so that our T statistic smaller and P value insignificant. Value insignificant. So you have to check. There are number of things you have to check after you estimate. You have to check whether it is significant or not, and then you have to check the sign of estimate whether it is consistent to the sign what we expect. If we expect positive, but we get negative, and then you need to do something lah. You cannot ignore the problem. Okay. So your equation will have good application power and suffer no problems other than artificially high standard error if the only problem is multi-quantity. Coefficient estimate will be unbiased. If you drop a variable, you may run into the problem associated with omitted variables. So if the problem is not that serious, and then you believe both x1 and x2, let's say that one, are important to explain the dependent variable y, then you can just ignore the problem as long as they are still significant, they are still having the same sign of estimate. Okay, because if both are important variable, explain why. If you drop any of them from the model, it's possible that your estimate is no longer unbiased, but it is biased estimate. Meaning that you have, when you drop any of the variable, then you have meaning that the average of your estimate is no longer equal to the true value. So it's no longer equal when you drop. So you have to make a careful decision. Okay, whether you really need to drop or not the variable. So only in the case of there is serious problem, then you drop it. Not then you not drop the important variable. And then some econometrician argue that if the model is otherwise okay, then just ignore it. Multi-variety increases the standard error of the estimation, hence making the t-statistic become smaller. If the t-statistic is big enough for us to reject, so coefficient to be statistically significant to reject the analysis, and the sign of the coefficient is still correct as what we expect, and then it shows that the issue of multiplicity is not that too serious, and then in this case we can just ignore the issue. Although your VIF greater than 10, and even though you check VIF greater than 10, you vary inflation factor. However, if the problem is so serious, just like the example that we had just now, and then you have to remove one of them, drop one or more of the coordinate variables. Another way is to drop one of the independent variable, which is the source of problem. Let's say S1 and S2 are strongly correlated, just like what we had the example that we had just now. Hence, we can only choose either S1 or S2 to be included or to retain in the model. Using theory, so which one we should retain? So you have to make again a decision. You should retain or to keep the more important variable to explain why, and drop the least important. Do not drop a variable strongly supported by theory. If you do this, you run the risk of having an omitted variable bias. So to review of omitted variables may make the estimate coefficient bias and standard error too small, and this problem is worse than having quality. Just now, so if you drop an important, very important variable to explain the dependent variable, then it's possible that the estimate that we have, or we produce estimate, the one that we call as a bias estimate. So the average of all possible estimate will not equal to the true value of the parameter. So for a given example, just now we have to drop. So we have VIF large that indicates for the serious problem, and then when we inspect the result or estimate, then we have one of them to have incorrect sign, p value significant, insignificant, and then contradict to this one, f and contradictory result of the f overall significant test and the individual significant test. So we need to drop one of them. So in this case, which one is more important? So you have to decide. So if we believe that income is more important to explain the consumption, then we drop the wealth variables. Okay. So if you drop one of them, so let's say we re-estimate the model without one of them. So quick estimate equation, then you can compare later on. So you have again consumption and income without wealth. Okay, just name equation 2. So you compare, this is the original one. Okay, this is, so this is the one after we exclude one of them. Well, so you see now, so this option. So this one, sign okay, Now this one significant. So unlike before, for the income P value not significant, is significant. But now after we exclude wealth, we have significant. Significant. So now we can say, we can conclude that there is significant influence of income on consumption. Okay. So this one, okay, I mean there's no diagram because only one variable left. Later we have another example. We have more than two variables in the model. If you estimate, if let's say you decide to remove income and then you just retain wealth, and then you see now it has a positive sign of estimate instead of negative, previously negative. Okay, and then it is significant as well. Okay, so you see the danger of having serious multi-cognitive problem. It leads us to the incorrect conclusion. It's supposed to be significant, but because of cognitive multi-cognitive, then it makes the estimate to be insignificant, not significant. Okay. The third possible way is to transform or define the variable. Sometimes the existence of multi-cognitive could be the result of misspecification of the model. So for the given example here, so let's say we want to explain, we want to model the number of cars sold annually, and then we use income, annual income, the annual household income, and then price. So it's times data, so average annual price of new cars. And because of the inflation, so income and price will strongly correlate over time because of both of them increases as the result of inflation. So because of this, it just like that the two variables are having strong correlation between them because they are both of them increasing the values. In terms of value, they are increasing because of the inflation. Okay. So hence we need to redesign the model to take into account of the effects of inflation in order to solve the problems of multi-cognitive. The way is by substituting the income and price with the inflation adjusted income and price variable. So that explained in the additional notes. How to adjust time series data for inflation. So let's say you have time series data, and then you can adjust, you can remove the inflation. What we call that, you can adjust for inflation, the effects of inflation, by using consumer price index, CPI. So the time series data that measure in currency value, such as income, GDP, tax revenue, and price, are increasing over time due to inflation. This phenomena will produce inaccurate education result. For example, let's say we want to construct a model using oil prices as a dependent variable and book prices as independent variable. And we will find that this is positive and significant relationship between the two variables. This, however, happens due to inflation, not because of the actual relationship between the two variables. Okay, they are keep increasing because of inflation, and then so meaning that they are basically there is no actual relationship at all between the two variables. But when we regress, we get positive, we get positively related. For example, because of debt, because of inflation. So you have to remove the influence of inflation first. So we need to remove the influence of inflation by adjusting the variables to get the real value. So for this purpose, use CPI, consumer price index, which measure value for certain goods from time to time. You can convert nominal value to the real value by using the formula. So nominal value divided by price index, and then divide by 100. Okay. So the example given here, so I say that the real or nominal, not the real, the nominal. So this normally we call as a current price. A current price. Data at current price. You refer to any as this one. They want the data at current price. They want a nominal price. So if you have the CPI and then you calculate like this, so you can see the real income after you remove the effects of inflation. So you see the difference lah. So although after 10 years, in terms of the actual amount it is increased, but in terms of the real value, just like the purchasing power lah, it is actually decreased. Okay. So if you have the data like that, and then try to remove the influence of inflation first before you estimate a model, in order to reduce the chance of having a multi-quality problem. And then the last one, increase sample size. The next factor to look at is the sample size, the number of observation. So if you are working with cross-section data, and you are undertaking a survey, you could increase the size of the sample by negotiating a bigger matrix. If you are working with time series data, you may be able to increase the sample by working with shorter time interval for data. For example, using quarterly or monthly data instead of annual, so that you have larger sample size. Increasing the data will provide more information for on a least square procedure. So meaning that it reduces the chance of having what we call that coincident linear dependence between variables. So let's say you have x1 and x2. Yes, now we have our variable x1, a list of x. If you have small data, you have small sample size, so there is a high possibility to have coincident relationship or linear relationship between variables. Let's say you only have 3, for example, let's say you have 3 variables, 3 observation, and then it's possible that for that 3 observation you have a coincident linear dependent. For example, this one x1 equal to 2 times of almost equal to the value of x2 plus x3, for example. So that is possible. When we have smaller sample size, the chance of having that linear dependence is higher, or we call as coincident linear dependent. So when, in order to reduce the chance of having that problem, then what we can do is increase the sample size. When we increase sample size, then we reduce the chance of having linear dependence between independent variables. Okay. Because now when we include more observation, then we have more variation in data. We have more variation, so let's reduce the chance of having coincident relationship between independent variables. So that one of possible way lah. So try to increase sample size if you have the problem. So if let's say you want to keep the variable, you believe that both are important, x1 and x2. So you want to keep both, but you have problems of linearity. So one way that you can do is try to increase sample size, okay, to reduce. If let's say the linearity happens because of the coincident what we call it, having similar values or linear related values between variables. Okay, so half an hour break. So we continue 7:53. Around there, 50 or 55, around there. Just before 8. We do lab session 2 and 4.